In this video, I'll show you how to determine the roundness and tilt of ellipses, and it's all in my book, Ellen's Guide to Perspective, on Amazon. We usually see vertical cylinders from a bird's eye view. So their ellipses are horizontal, meaning that their major axis is horizontal, and the minor axis is contiguous with the axis of the cylinder. The top ellipse is narrower than the base because it's closer to eye level, and at eye level, the ellipse is a line. For a horizontal cylinder, the ellipses are vertical, meaning the major axis is vertical, and the minor axis is still contiguous with the axis of the cylinder. The ellipses narrow as they get closer to the central vertical line. Here again we have the eye and the line of sight going to the center of vision, which lies on the picture plane, that transparent vertical plane. The distance from the eye to the ground line is the height of the eye, or the height of the viewer. Now, if we took this center of vision and used it as a center of the circle and started here at the eye and circled our way down here, where it intersects this vertical line would be the nadir. So the distance between the eye and the center of vision is identical to the distance between the center of vision and the nadir. This is an overhead view of glasses on a shelf. So let's find the center of vision and the nadir. The center of vision is also the center of an uncropped photo where the diagonals cross. Where's the nadir? Well, if we follow the perspective lines of the picture, we will come to the nadir, which is the vanishing point for the whole picture, and it's vertically below the center of vision. Now that we found the center of vision in the nadir, we can see that this actually isn't quite an overhead view, because if it were, the nadir would have to be hidden behind the center of vision, so we wouldn't see it. There's even more we can learn from this overhead view. When is a glass opening a circle? When its center is at the center of vision and when it is perpendicular to our line of sight. So a glass here would be pretty much a circle, although I said this was not quite an overhead view, so our line of sight isn't quite perpendicular to the picture plane, but a glass would be almost circular at this point. Ellipses around it get more circular as they approach the center of vision. Now let's look at these blue axes. They all point toward the nadir, and the magenta axes circle around the nadir because they always must be perpendicular to the blue axes. So if we want to know how round an ellipse is, we need to know how close it is to the center of vision. If we want to know how an ellipse tilts, we have to find the nadir. This is a view looking directly up at glasses on a glass shelf. So these are the bottoms of the glasses. I was able to get the center of vision and the nadir to coincide. The center of vision is where the diagonals cross in an uncropped photo. The nadir is where the perspective lines for the pictures meet. So it's the vanishing point for the pictures. You can see that the axes of the ellipses converge toward the nadir. What happens in a bird's eye view? Well, eye level is the same because it's the distance of the eye above the ground. But now the line of sight angles down, so we have a new center of vision below the original one, still on the central vertical line, but it's no longer on eye level. When we use this original center of vision as the center of a circle, we got a nadir here for an eye-level viewpoint looking straight ahead. Now, if we use this as our center of the circle for a bird's eye view, we would circle down like this and we would get a new nadir for the bird's eye view. So the distance between the center of vision and this new center of vision is the same as the distance between the nadir for the eye-level view and the nadir for the bird's eye view. Here are glasses seen from a bird's eye view, looking down at them. The center of vision, again, is the center of an uncropped photo. But there are no circles there because the openings of the glasses aren't perpendicular to our line of sight. We're seeing them from the side. Now, the nadir is where the perspective lines of the picture go. You can see here and here. But it is also the direction of the minor axes of the ellipses. A worm's eye view is the opposite of a bird's eye view. Here we're looking up at the glasses. So the center of vision is again the center of an uncropped photo, and the perspective lines go to this point up here, as do the minor axes of the ellipses. And although it's the highest point, I'm still going to call it the nadir, just to be consistent with the rest of the pictures. Let's look at these three glasses in a row, which are in a frontal viewpoint. This is the center of vision, which is the center of the photo, where our line of sight meets the picture plane. The bottom of this middle glass is a circle because its center is at the center of vision, and the openings get more circular as they approach the center of vision. The minor axes point toward the nadir and coincide with the axes of the cylinders, and the ellipses tilt up as they circle around the nadir. Here are three glasses in a row, and here are three glasses on different planes. Now, in the first case, the cylinder axes point toward the nadir and become more horizontal with distance. As a result, these elliptical major axes, which must remain perpendicular to these cylinder axes, tilt up. Now, where is the center of vision? Well, this is nearly a circle, so the center of vision is probably around here. For ellipses on different planes, we again see ellipses tilting up with distance because they must remain perpendicular to the cylinder axes. But this one is rounder than this one down here because this distant one is closer to the center of vision. I put all the axes on these elliptical logs, and let's see what it tells us. So this is probably the roundest log, and so we can determine that that's about where the center of vision would be. And the x-axis, or the horizontal axis, is eye level, and the vertical axis is the central vertical line. Now, for the minor axes of all these other ellipses, you can see that they get more horizontal as they approach the center of vision. The major axes, these blue axes, become more vertical as they approach the center of vision. And if you were to follow them down, you would find that they all converge toward the nadir. Although these are identical cups, they appear to narrow as they recede, going from about a 25-degree ellipse in front to a 10-degree ellipse in back. Foreshortening is the shrinkage of dimension into depth more than width. So the minor axes here diminish by about 2/3 with distance, whereas the major axes only diminish by less than half, and the result is a narrowing of the horizontal ellipses. In my next video, I'll show you how ellipses show depth, and please remember to subscribe.